Good afternoon, guys. Welcome to our talk. Let me introduce myself. So, my name is Masood Rahman. I'm an assistant professor at Dalhousie University. So, this is a collaborative work with Polytechnic Montreal and University of Saskatchewan. And these are my co-authors. So, Futscom is a professor from Polytechnic Montreal. Then Shamima Yasmin is a PhD candidate from University of Saskatchewan. And Chonchol Roy is a professor from University of Saskatchewan as well. So this talk is about bug localization and query reformulation. So that means we are going to talk about software bugs. And software bugs were there from the very beginning of software engineering, right? But in this talk, I am going to present a bit much more recent statistics. So in 2017, more than 600 bugs were recorded from different companies. And these bugs cost about $1.7 trillion to the global economy. And they also affected more than 3.7 billion people. Now, these are obviously very strong numbers, and the developers also spend like 50% of their development time to deal with bugs. And as you might know, that the process of finding and fixing the software bugs is called software debugging. And there are three different stages in software debugging. So first is bug localization. That means first you need to find the location of the bug. And then the second step is bug understanding. That means you need to understand the dynamic behavior of the bug using different technique like bug reproduction. And then finally, the actual bug fixing. That means you need to correct the faulty code. So these are the three different steps, but in today's talk, I am going to mostly focus on bug localization. Now, if you are hearing this phrase called bug localization for the first time, then this example is for you. So let's say this is an example bug report, and this bug report is talking about some kind of bug, but that bug is hidden somewhere within the code. Now the process of finding the location of the bug within that code base is called bug localization. Now in this talk, I am going to focus on a specific type of bug localization called IR-based bug localization. And if you're hearing the term called information retrieval for or IR for the first time, think about Google search. So in the Google search, you select a query, and against that query, you get a bunch of relevant results. So similarly, in the case of IR-based bug localization, the bug report will be used as a query to find the buggy code from the code base. So what many folks did, they considered this bug report as a kind of search query, and then they will execute this query with a code search engine like Lucene, and then the Lucene will return a ranked list of results, and the expectation is that the buggy code will be at the top position of that result list. But that does not happen all the time. It's because you see that the bug report is not written to be used as a search query, right? So what many folks did, rather than using this whole bug report as a search query, they try to come up with a subset of keywords to formulate a query, and then they will execute this query to find the buggy code at the topmost position. So this is how the IR-based bug localization works. And I am going to focus only the specific part, that is the query reformulation part. So let's say this is our bug report, and you see that it contains lots of structural information. And sometimes it might also not contain any kind of structural information like this. Now the process of selecting appropriate keywords from that bug report to formulate a query is called query reformulation in the context of bug localization. And this is going to be the focus of my today's talk. And selecting appropriate query from the bug report is not an easy task as well. A study shows that about 88% of the times developers fail to choose the right keywords from the bug report. So this is obviously an interesting research problem. And we are going to drill down on this research problem in our today's talk. So what we have done is we divided our analysis into three different research questions. And in the first research question, we try to understand that how the existing IR-based bug localization techniques use query reformulation. That means if we apply the state-of-the-art query reformulation techniques in the context of IR-based bug localization, how do they perform? So that is the focus of the first research question. Then in the second research question, we try to find out whether the bug reports actually contain any meaningful search queries that we are looking for, right? So if the bug reports do not contain any meaningful keywords, then we cannot form the query. So that is the focus. We try to see whether the bug reports actually contain any meaningful keywords or not. Then in the third research question, we try to differentiate between optimal and near optimal search queries. So from the first two research question, we found that there could be some optimal and there could be some non-optimal keywords and queries. So in the third research question, we try to differentiate between these optimal and non-optimal search queries using different kind of characteristics. Okay, so this is a kind of workflow of our study. And as you can see, we have collected bug reports from the bug tracking system. Then we also collected bug fixing commits from the version control history. And then we did a bit of linking between this bug report and this bug fixing commits. And we also did a lot of filtration. And the detailed steps can be found in the paper. I would highly encourage you guys to read the paper. And then we get a refined data set. And using this data set, we try to answer the three research questions that we have. And then we come up with our finding summary. So let me start with the first research question. But before that, let me also talk about the data set that we used. So we selected 6 subject system. And we collected more than 2,000 bug reports from those 6 subject systems. And we also used 4 performance metrics like hit at K, then mean reciprocal rank, then mean average precision, as well as query effectiveness. And you might also hear this term called baseline queries in the coming slides. So when I say baseline queries, what I mean is the pre-processed version of the bug report and used as a search query. So in the bug report, you have title and you have also the description. So in the baseline query, basically use the pre-processed version of the title and description as our search query. Okay, so let's talk about our first research question. And in the first research question, we use different kind of query reformulation techniques in the context of bug localization. And from the literature, what we have found that there are two major themes for query formulation in the context of bug localization. One is frequency based and another is graph based. So for the frequency based techniques, what these folks did, so they will capture a bug report, and from that bug report they will calculate the term frequency as well as the inverse document frequency of different keywords, and based on this TF-IDF, they will try to determine the importance of different keywords, and then the important keywords will be extracted as a search query. On the other hand, in the case of graph-based techniques, what we have found is that many people converted these bug report into some kind of text graph like this based on word co-occurrence or parts of speech dependencies. And then they will use some kind of graph-based term weighting techniques like PageRank algorithm to identify the most important nodes from this graph. And then those important nodes will make the query for that bug report. And then that query will be used for bug localization. Now, let's talk about our first research question. And this is the findings from our first research question. And what you can see the performance of baseline search queries. Then you can also see the performance of keyword-based query selection techniques as well as the graph-based keyword selection techniques. And what you can see here is that the state-of-the-art techniques are not able to outperform the baseline techniques. So, which is a kind of shocking result. But we did a bit more investigation, and what we have found is that the baseline queries are containing on average like 50 keywords. On the other hand, these state-of-the-art techniques are delivering only, let's say, top 10 keywords. So that means this guy over here is delivering comparable performance using only 1/5 of the baseline keywords, right? So yeah, so that's a kind of makes sense, but we did a bit more investigation using our data set, and we found that the bug reports can have different type of properties. That means we see that some bug reports, when they are pre-processed, they can automatically lead to high quality baseline queries. So for example, you see for like 2/3 of our bug reports, we found that the baseline queries themselves are leading to very high quality, leading to very very good performance. So for example, for these 2/3 of our bug report, we found that the baseline queries can achieve like 100% hit rate, which is very interesting. But then we also found that for about 34% of the bug reports from our data set, the baseline queries are performing very poorly. And we see that for that 34% of the bug reports, the baseline queries were not able to return any relevant result within their top 10 position. So which is kind of interesting, right? So yeah, so that means the baseline queries are performing well, mostly because of this 2/3 of the bug reports. Okay, so then comes our second research question. So from the first research question, we found that at least 1/3 of the bug reports are not leading to high quality baseline queries. So that means, do they actually contain any meaningful keywords or not, right? So that is something we try to investigate in our second research question. And for that, we use genetic algorithm. And using genetic algorithm, we try to identify some optimal keywords. And this is how we have done it. So first we take a bug report, and from that bug report, we extract all the individual keywords. And then from that individual keywords, we generate population. And in that population, each individual is basically a combination of multiple keywords, right? Now, if you have a bit of experience with genetic algorithm, you will know that this population will now go through different kind of genetic operation like selection, then crossover, then mutation, and then there will be the fitness calculation. And what we use for fitness calculation is query effectiveness and mean average precision. And obviously, this is a kind of iterative process, so it will go through multiple generation, and finally will come up with an optimal search query from this bug report. So let me also give you an example. So let's say this is our bug report and this is the optimal query. Now, when I say optimal query, what it means is that this query can return the buggy code at the topmost position of its ranked result. Okay, now let's take a look at the findings from our second research question. And what we found is quite interesting. So this is the result. This is a kind of comparison between baseline queries and the optimal queries that are generated using genetic algorithm. And what you see is that the baseline queries were able to achieve like 32% hit at 1. On the other hand, these optimal queries can achieve like 87% hit at 1, which is quite interesting. And this result is for the whole data set. And then we also investigate for the two subset of our data set for which the baseline queries were performing very poorly, and this is our findings. So as you can see that for this 1/3 of our data set, the baseline queries were performing very poorly, but the optimal queries that are generated using genetic algorithm, they are performing very their performance is very high, and which is pretty interesting. So what we can suggest from this finding is that for about 1/3 of our bug reports, the baseline techniques, those bug reports are leading to poor baseline queries, and even the state-of-the-art techniques are not able to deliver high-quality search queries from that 1/3 of our dataset. But interestingly, these bug reports also contain some meaningful keywords, and those meaningful keywords could lead to some kind of optimal queries. And this is the evidence that we are seeing here. Okay, so guys, at this point, we know that the state-of-the-art techniques might not be sufficient to deliver search queries from all bug reports. And although they are not sufficient, there are actually some meaningful keywords in most of the bug reports. So that means there are optimal search queries and there are non-optimal search queries, right? So in the third research question, we try to differentiate between this optimal and non-optimal search queries. And this is the data set that we used. So we used more than 13,000 search queries and around 5,000 optimal search queries and around 5,000 non-optimal search queries. And when I say optimal query, that means the query can return the buggy code at the topmost position. And if the query cannot return the buggy code within the top 10 position of its result, then that query is considered as non-optimal. So what we did, we collect like 31 different properties, linguistic as well as syntactic properties from the search queries, from both optimal and non-optimal search queries. And then we try to differentiate between these queries using machine learning as well as qualitative analysis. And for that, we use random forest for our classification, and this is the performance. So you see, using that 31 characteristics, our random forest algorithm can classify these two different queries quite well. So we see the precision and recall both are close to 80%, right? So that's pretty interesting. And when we do the feature importance analysis, what we found is that the optimal keywords and the non-optimal keywords could be quite different in terms of their frequency, then entropy, then the location, as well as parts of speech. So we did a bit of distribution analysis as well, and we found that the distribution of these four different features that we talked about are quite different for optimal and non-optimal search queries. And we also used statistical significance tests to determine their significance, and we found that they are statistically significant. So they are significantly different. Then we also did a bit of regression analysis, and what we found is that the term frequency and the entropy might not be a good indicator of optimality, but these two other guys, that is the body keyword ratio and the noun ratio, these are quite interesting indicator of optimality. So this is our actionable insights that we found, is that the optimal keywords are less frequent than the non-optimal keywords in a bug report. Then the optimal keywords are less ambiguous than the non-optimal ones in a bug report. Then we also found that the optimal keywords are more likely to be found in the body section, and the optimal keywords are more likely to be noun. So so we use these actionable insights and we repeat our experiment, and what we found is interesting. So what we found is that we are able to improve the performance of the baseline queries for those two subsets significantly. So as you can see, the baseline hit at 10 was 0%, and now it is 16%. And the similar thing goes also for the state of the search queries. We are also able to improve the performance of the state of the art queries as well. Okay, guys, so these are the take home message. So around 34% of the bug reports could lead to very poor baseline queries, and even the state of the art technique are not sufficient to deal with them. But using genetic algorithm, we show that these bug reports actually contain some meaningful keywords, and the optimal and non-optimal keywords could be quite different in terms of different properties. and we were able to improve the performance using our actionable insights. And these are the actionable insights. These are the open research problem.